Fagor Automation, open to your world.
Welcome. Up now, we have Fagor Automation, an international CNC system and high-accuracy encoder manufacturer for the automation industry, and a member of ADIMAT, the Additive Technology Research Alliance. Representing Fagor Automation today, we have Ryan Adamovic, the Senior Market Coordinator for North America. Ryan has been with Fagor Automation since 2018 and uses his background in business management and digital marketing, media marketing to present manufacturing technology as a business solution for all skill levels. This presentation also features insights from Diversified Machine Systems, an American 5-axis router manufacturer and hybrid machining solution provider. Together, they will be discussing how flexibility is key for additive manufacturing. Before we get into the presentation, if you have questions for the presenters, please type those into the Q&A box found at the bottom of your screen, and we will get to as many as possible. Now, on to the presentation.
Thank you, Elizabeth. Hello. I'm Ryan Adamovic, Senior Marketing Coordinator of Fagor Automation North America, and welcome to our November 2021 Manufacturing Lunch and Learn presentation. For the last presentation, we discussed our new portable user interface built with HTML5. A human-machine interface that is web-based for ease of portability, customization, and compatibility with IIoT technologies. These attributes really encompass our company's motto, being open to your world, about being flexible to the individual needs of the manufacturing industry. Specialized needs are required across this industry, especially when it comes to unique technologies like additive manufacturing. Industrial additive manufacturing has evolved into a consumption-effective and versatile solution for aerospace, automotive, defense, and rapid prototyping sectors. Today, we'll be looking into why flexibility is so important when it comes to implementing additive manufacturing technologies. We'll be discussing what Fagor Automation's role is when it comes to additive manufacturing applications, concerning on how we work with machine tool manufacturers to integrate custom features, programs, and functionalities into a control system for additive and hybrid applications. For this presentation, we will also have Nathan Dix of Diversified Machine Systems to discuss their hybrid additive advancements and how it has been used. Based in Colorado Springs, Diversified Machine Systems is an American industry-leading designer and manufacturer of 3 to 5-axis CNC routers, machining solutions, and hybrid additive technology. As always, this presentation is pre-recorded, but both Fagor and DMS will be answering questions live at the end of the presentation. Before we jump into our presentation, we wanted to familiarize you with our company as a whole and what we do. Fagor Automation is part of the Mondragon Corporation, one of the world's largest employee-owned cooperatives. The key takeaway from this is the number of resources this gives Fagor. Mondragon has 15 full-size technology centers that constantly do R&D. In fact, at least 10% of Mondragon and Fagor's profit gets invested each year into R&D. The Mondragon Corporation also manages the University of Mondragon in Spain. Mondragon also partners with the University of Basque Country that has a research group for additive manufacturing. In October of 2020, Fortune magazine declared Mondragon Corporation as the 11th most important company in making change in the world. Last year was Fagor Automation's 45th anniversary. For those 45 years, we've been one of the leading providers for machine automation and control products. We provide CNC systems, linear encoders, angular encoders, servo drives and motors, and digital readouts, meaning we are one of the few existing companies to be a single source solution provider for both CNC controls, feedback devices, and servo drives and motors. As of right now, Fagor offers 3 main Windows-based CNC system models. The 8058 for small or medium-sized machines up to 4 axis, and the 8060, designed for high-speed precision machines up to 10 axis, and our 8065, our top-of-the-line 32-axis control for complex machines like 5-axis machining centers, gantry mills, and boring mills. However, all of these control systems were designed with features tailored for milling or turning. Unless you're doing hybrid machining, you don't necessarily need all the functionalities and algorithms that come with the 8065M, and you're also missing out on the ability to create your own specific functions. We converted our most powerful control system, the 8065, to an open-line system, the 8070OL. The 8070OL is designed not only for additives, but is also capable of easily tackling all kinds of applications, such as grinders, saws, press brakes, and cutting applications such as wood, marble, laser, stone, glass, and plasma. Both the 8065 and the 8070 utilize our Q7 CNC platform, built for the current and next generation of manufacturing engineers and machinists in mind. The quad-core processor and 16 gigabyte NAND flash memory ensures lightning-fast data processing speeds, efficiently storing the data while running complex toolpaths. Also available up to 128 gigabytes of CFast solid-state memory. Research is one of the cornerstones of Fagor Automation. We are mindful that companies are always looking to move forward towards the future, so it's important that we are prepared for what may come next. That's why when it comes to additive manufacturing, we have partnered with several companies and associations to further expand our 3D capabilities. Associations such as ADIMAT, the Spanish Association of Additive and 3D Manufacturing Technologies, LoreTech, a private technology center that specializes in metal additive manufacturing, and Diversified Machine Systems, one of the leading hybrid additive machine tool makers. With these partners, Fagor Automation is able to participate in several non-commercial additive research projects. These projects help generate the knowledge and features we will be going over in today's presentation. The EUSK ADDI project involved partnering with other members of the ADIMAT group to develop mechatronic devices used in the manufacturing process of filler materials using plasma, laser, and thermal projection. With the CNC LMD project, we were able to strengthen our laser metal deposition functionalities for the management of different parameters such as melting pool temperatures, powder flow, and laser power control. The goal of the Proclama project was to achieve a zero-defect process for LMD by creating new advanced control strategies. With Addiscend, research was conducted on different processes of the additive manufacturing technologies, such as LMD, hWAAM, and material extrusion. Lastly, Virginia Tech has been utilizing a DMS hybrid additive machine equipped with the Fagor 8065 to develop new deposition strategies for directed energy deposition. As I'm sure most people watching are already familiar with what additive manufacturing is, I'll just summarize. Whereas how traditional subtractive manufacturing is cutting away material to make a part, additive manufacturing instead adds material layer by layer in order to create a part. According to ASTM F2792 standards, there are 7 different forms of additive manufacturing. Methods like powder bed fusion are fantastic for rapid prototyping. Material extrusion is inexpensive and can be used in an office environment. But what we're going to be focusing on is directed energy deposition. Over the last decade or so, we've observed this method to be the strongest for industrial metal additive manufacturing, the goal of which is to produce reliable and reproducible parts that are fully functional. Directed energy deposition, DED, is where metal wire or powdered material is extruded from the nozzle and is hit with high-powered energy, such as lasers or welding, to bond it into a single layer. This is the most mature method of additive manufacturing. This is used for very specific and accurate parts, such as creating a very light yet strong titanium alloy limb, to creating large, complex parts that would otherwise require machining most of the material away. Most of the time, DED doesn't require machining after printing, only light post-processing, and accuracy depends on the nozzle, laser beam intensity, and the material. Materials include alloys, ceramics, and composites like carbon. Out of all the methods of industrial additive manufacturing, DED has some of the highest single-point deposition rates, leading to the fastest additive production times. One of the more common forms of DED we work with is laser metal deposition, LMD. You can use materials such as steel, titanium, tungsten, chromium, any metal or alloy that you can make a powder of and inject through the nozzle. The material is deposited through a nozzle into the target area, known as a melt pool, where it is then hit with a laser beam that melts the material to bond into a part. The material is dispensed layer by layer to create medium to large size complex parts. This process is efficient with a 70 to 90% material efficacy, meaning only the necessary material in required areas are used, thus reducing waste. We've observed this technology being used for turbo machinery, where large complex shapes used in turbines can now be produced with a purely additive method. The Fagor CNC system plays a big role during this process. Due to its open design and multi-process support, it effectively regulates melting pool temperature, regular layer deposition, laser power, continuous toolpath movement, and powder flow. We've also developed specific tools for LMD. We've introduced a technological materials and parameter table system. The information related to materials and the additive process is organized to provide a simple and intuitive management of all the process-related data. We have made this fully customizable by the machine builder or a high-level user. Also used in our laser cutting controls, we have pulse width modulation. This is used to control the operating cycle of the laser signal, allowing the user to modify the laser beam power. With our control, you can also control the laser power depending on the speed of the laser nozzle path, allowing to maintain a smooth and uniform deposition. Lastly, we have closed loop process control. Any PID loop that you can process, you can integrate easily in the Fagor control system. The Fagor CNC can read C programming language files with custom PID loops written in. All these features are bundled together in our additive pack. Something we get asked a lot is, why is a CNC system required for additive machines? Binder jetting and 3D printers don't require CNC controls and can be purchased at low prices. Again, this comes down to what you're trying to accomplish with your application. If you're looking for rapid prototyping and low-risk parts, perhaps a CNC control might not be required. But for fully functional parts that are reproducible and reliable, it wouldn't be advisable to use an economic motion controller instead of a complex CNC system like the 8070OL. For a high-quality DED machine that doesn't have hybrid machining capabilities, there are 3 requirements that need to be addressed to achieve accurate and reliable parts that are within an acceptable tolerance. Your controller needs to be fully capable of accurate positioning and contouring. It is essential to have multiple axes working simultaneously to get that accurate contouring. A regular control has difficulty following a contour path on rounded corners. You need a CNC to program that curve and execute it both accurately and fast. Your controller needs to have a reliable way of controlling the laser beam's pulse width modulation. For directed energy deposition, you're modulating the pulse width of the laser beam sequence and synchronizing it with the motion. Some motion controllers give you the ability to develop your own way of controlling pulse width modulation, but Fagor gives you everything you need for pulse width modulation instead of having to have you develop your own. Lastly, the controller needs a PLC to control the input-output and to control the safety all in real time. Being able to integrate PID loops to control process metrics is a key feature that separates high-quality LMD machines with entry-level LMD machines. Also, having collision detection and a safe work zone setup can make the process even safer. These three requirements help achieve the quality needed for fully functional and repeatable aerospace, automotive, medical, and defense parts. We also work very closely with another additive process in the DED subcategories called Wire Arc Additive Manufacturing, hWAAM, otherwise known as gas metal arc welding. Instead of powder being melted with a laser, hWAAM uses an electric arc to weld the metal wire directly to the surface. hWAAM is used to manufacture large-scale metal parts quickly and at less cost. There is no size limit to this method beyond the working space of the welding equipment. The welding wire is more readily available than metal powder, and while laser metal deposition has a high deposition rate of 2.5 kilograms per hour, hWAAM can deposit steel even faster at 4 kilograms per hour. How does this process work? A thin metal wire is fed through the spool through the tool nozzle. When the welding current is triggered, an electric arc forms between the metal wire and the workpiece and melts both metals above their melting point, causing the metals to join together in a single piece. Shielding gas also flows out of the nozzle to prevent the metal from reacting to oxygen while melting. While deposition rate is much faster than LMD, the workpiece has a much lower resolution initially with hWAAM. However, hWAAM is much more conducive to interpass decking, hybrid machining, to create more complex geometric structures with precision finishes. Hybrid machining is using directed energy deposition to add the material to the part, combined with CNC machining to finish the part as it's being printed. By using both additive and subtractive manufacturing on every layer, you can achieve smooth surface finishes, faster production times, and more complex parts. One of the leading providers of hybrid machines is Diversified Machine Systems, located in Colorado Springs. Fagor has worked very closely with DMS over 20 years to create a customized automation solution for their machine line. Here to speak on behalf of DMS is Nathan Dix.
I'm Nathan Dix. I'm the Product Development Manager here at DMS. I've been focused pretty heavily on the hybrid machines and specifically on our metal additive line. So I help with the machine design, I do the parameter development for the deposition, I help with customers on case studies to see if their parts make sense for additive. One of the unique things about our product is we're really one of the few people, one of the only OEMs I'm aware of that have integrated a wire arc additive process into a subtractive machining center. So there's other people around that will do retrofits for you. They'll add 3D printing to your existing machine, but we're an OEM and we're designing these machines from the ground up for hybrid applications. This machine behind me is a good example of that. It's a custom machine for us. It's a 5-axis machine with a tilt-rotate table and a 1200 millimeter diameter on that table. Since we've designed this machine from the ground up, we're able to include cooling of the table. We're able to include a rotary slip ring in the table to get the ground to the table. So just little things like that we're able to do that really make the machine a more complete package. We have 2 standard lines right now. We have our Hero line, which has a 2 foot by 2 foot by 2 foot build volume. It's designed to deposit and machine aluminum. There are upgrades for that machine to let it deposit and machine stainless steel. And there's also an optional 5-axis tilt-rotate table that we can add to those machines. That tilt-rotate table is mounted on linear rails and you can slide it in and out of the build volume, so you can either have the full 2 foot by 2 foot 3-axis area, or you can slide in the 5-axis table and have a 15-inch diameter, 15-inch tall cylindrical build volume. That machine is really focused towards kind of learning about the process development. People that are interested in hybrid, maybe not ready to get a big machine or do full-scale parts, we steer them towards the 2-cubed just to kind of learn how the process works with their parts. And it's been a successful machine for us. A newer machine line that we've just launched is our Liberty series. We have a 600 and a 1200. The 1200 is behind me. It has the 1200 millimeter table with true 5-axis deposition. The 600 is very similar, but it has a 600 millimeter table. Both of these machines have been designed with the stiffness required to print and machine many different materials ranging from aluminum all the way up to stainless steel. Right now, we've had a lot of interest in the military, DoD. They're interested in making new types of parts, and they're also interested in making replacement parts. One of our machines was just recently purchased by an artist. He's planning to 3D print large aluminum sculptures. We've also had a lot of interest in various industry segments where they're traditionally manufacturing things with casting, and for these low volume castings it makes more sense to print it than to have it cast in some cases. We've seen a lot of interest in the hybrid machines for a few different applications. We have a lot of customers that are interested in obsolete parts. They have a part that's failed, they're looking for a way to make that that's more quick than traditional manufacturing methods. One really good example of how we use this hybrid technology here at DMS is this 5-axis yoke that we made for one of our large custom 3D printers. I always enjoy 3D printing parts that we use on the 3D printers. I think that's really fun. This particular one, we've built 2 of these machines. On the first machine, we built this yoke out of individual aluminum plates that we bolted together. It was 7 or 8 individual piece parts that we bolted together, something like 20 or 30 pieces of hardware to join all of these together. And then you end up with tolerance stack up, just a complicated solution to this problem. When we sold a second one of these machines, I took the opportunity to redesign this part from the ground up to be manufactured with our hybrid machine. So I placed the components I needed. This is a 5-axis yoke, so it has a gearbox and it has an electric motor to drive that gearbox. I just placed those in space, and then following the additive design rules, I added the material I needed to mount those, and we ended up with a stronger part, a lighter part, and we went from 8 components to 1. We also see customers with very complex geometries that you can't normally make easily with a completely subtractive process. With a hybrid machine, we're able to build some of the part, stop, do machining operations, and continue building. So we're able to get fully machined surfaces on the inside of parts that it would be impossible to do with any other method. Fagor has been a good partner in the development of these machines at DMS. They're my first stop when I'm speccing out a custom machine like this. The customer says they want it. I go to his office and say, hey, can you guys supply drives and a controller that will make this work? And then he's able to help us at every step through the process when we commission a machine like this. The controller, we also have some custom hybrid screens that we've implemented on the controller for things like communications with the printing process, things that make it easier for the operator to do the additive process. We've actually modified the auto screen that you see while you're running a program, and it has some adaptive controls in there that you control. It shows the layer height. Things like that have really helped us make this product what it is.
Thank you, Nathan. We hope you enjoyed our presentation and learned something new about all the technology that goes into the industrial additive machinery of today. Both Fagor and DMS will now be taking questions live. Thank you.
I will start this one off. I believe we have Ryan, Nathan, and then I believe Artur Gugolski and Thiago Miranda have joined us. So the first question, how does the control monitor the melting pool temperature?
Yes, yeah, I can answer this one. The melting temperature is something people want to see and read because of the part of the process they're doing for printing, for the printing part. So we offer different ways to connect different type of temperature sensors. Our customers use thermocouple sensors. They use inspection or temperature cameras. So the information with the camera is translated into a temperature reading using the algorithms for image processing. This is part of the typically the camera will come with this kind of algorithm. And now the CNC system can read the value of the temperature and create PID loop or other algorithms, high-speed PLC algorithms to control the temperature setting points by adjusting the power or changing the, possibly the power is okay, but you just adjust the deposition rates, feed rates. You can slow down or speed up to follow the temperature.
Perfect, thank you. And Nathan, I'm thinking that this question would be directed to you. What is the largest piece that you are aware of that's been done with DMS hybrid machine?
The largest machine we make is 6 foot by 12 foot with 4 foot build height. And the biggest part that they made on that was 8 foot long, 21 inches in diameter. It was a prototype unmanned underwater vehicle.
Great. And whomever would like to jump in on this next question, we still got a few minutes left. What protocols does the Fagor control have to connect with external peripherals?
I can answer this one.
Great.
So Fagor has several protocols to connect to the external world, including like EtherCAT bus, Ethernet, CAN open, Circus 2, Circus 3. We also offer like USB ports like USB 3.0, feedback inputs for like TTL, 1 volt peak to peak, SSI base, like and that like several protocols. Also high-speed inputs for probe connection as well.
Wonderful. Thank you for that. And again, whomever would like to jump in, what milling features and algorithms are useful when it comes to hybrid machining?
Yes, yeah, I can probably offer you
Great, Artur.
Yes. So the answer is, in this case, our experience working with the milling 5-axis algorithm for motion, machine motion, are playing a key role for additive part as well. So in the hybrid machines, it's critical to control the 5-axis motion, not only for milling, but also for deposition. So we offer high-speed algorithms for making it follow the path as quickly as possible. We offer a machine kinematics, very quick way to set up and calibrate the machine. Many of those machines have a complex tables, complex relationship between the head and the part. And it's very critical to be able to calibrate properly and quickly the kinematics definitions. Also, the whole machine can be calibrated using our compensation tables. We offer least screw compensation, cross compensation, volumetric compensation. All those algorithms working together create a great tool to not only mill the parts, but also the position, create the build. Many, I think what Nathan was also saying, but many of those machines have very complex configurations. You can have a table spinning, rotating the part. You can have also head rotating the deposition head. So experience working with 5-axis machining will benefits here with the 3D printers hybrid approach.
Does sound like it. Well, gentlemen, it looks like we have reached the 1 o'clock hour in my time zone, at least. And that is going to wrap up today's manufacturing lunch and learn, but I would like to thank everyone for attending and just remind everyone that we will include a recording in a post-event email, so you'll be able to watch this on demand anytime. Thanks for your attention today, everyone. Have a great afternoon.
Thank you.